Okay, so last lecture we concluded our small signal analysis. In particular, we said that we would, for each individual single stage amplifier, we found out how to make a equivalent circuit model that included an input resistance, a gain, and then this would be plus minus V in, then V in, plus minus. So this is a voltage controlled voltage source, and then an output resistance R out. And then we said that what we connect to this particular circuit will actually be a load RL and then a voltage source which is going to have a resistance associated with it, and then that would be our equivalent circuit model for each of these circuits. So in particular, we studied three um, configurations, and these configurations were the common source configuration, and we derived what the input resistance was, the output resistance was, so input, output, AVI. Additionally, we derived what the total gain is, or the gain, the voltage, the gain across including the RL. And then we also did this for the common drain, and we did this for the common gate. So at this point, you should be able to derive all of these if you're given a circuit. You will most likely be asked to do that in an exam. And in particular, we said that first we were gonna replace our transistor with our small signal model, which is basically, so if this is the source, if this is the drain, and this is the gate, then you have a voltage controlled current source, GM VGS plus minus VGS, and then there is a little RO associated with the channel length modulation. And then we said we were going to replace our transistors with this pi model, and then we were going to derive our Okay, additionally, we will actually go into our what we call the high frequency regime. And in particular, so in the previous slide, we said, hey, if we keep increasing the frequency of our uh, small signal, eventually we can treat all capacitors as short, external capacitors as short. But as it turns out, if we keep increasing the frequency beyond that, we're going to experience some non-ideality from our MOS circuits. So if you recollect, when we looked at the geometry of our MOS transistors, we had this conducting layer on the top, and this conducting layer would this conducting layer would one second, my pen is failing. This conducting layer would accumulate charges, which would cause an electric field, and that electric field would lead to the generation of the channel. Now, as it turns out, that double layer of charges is actually a capacitance. So as it turns out, there's a capacitance between the gate and the source, and then there's a capacitance between the gate and the drain. And so if we keep increasing the frequency of our MOS transistors, eventually we're going to have to not treat those as open circuits, but treat them as capacitances. And if we, but we don't have to do that for a wide range of frequencies because these capacitances are extremely small. So they're between a picofarad or 10 to the negative 12 and a femtofarad or 10 to the negative 15, whereas the external capacitances can be in the order of micro or 10 to the negative 6. So they're quite a few orders of magnitude smaller than the external capacitors. So as it turns out, there's a nice range where we can assume that the external capacitors are short while still treating the MOS capacitances as open. But if we keep increasing the frequency, eventually these MOS capacitances will start behaving as short and our amplifier will stop working. So as a result, there is kind of a limited band of performance. Okay, in particular, what we're going to actually do when we try to figure out what these frequencies are is we're going to actually try to find the R Thevenin looking into each of the capacitor terminals. to determine what the equivalent resistance is that each capacitor sees. And then what we're going to say, well, if the impedance associated with the capacitor is less than R, so 1 over j omega c, then we can treat the capacitor as an open circuit. Sorry, so basically if 1 over j omega c is greater than R, then we say it's humongous. And so we can treat the capacitor as an open circuit. But then if R is less than 1 over j omega c, we can treat it as a short. Meaning that if R is the one that dominates in the circuit, we can approximate the capacitor as a short. So here I look at that same equation, but for different values of tau. And as you can see, as tau as tau decreases, so going up, this thing moves faster and faster to the final value of 5 volts. Now, so what that means is that the smaller that C is, the more that this circuit behaves as an open, or for a higher range of frequencies that this will behave as an open. Now, of course, that's true because if you look at this, 1 over j omega c, and our condition for it to behave as an open was that this has to be greater to this process. Okay, so just to reiterate, a capacitor has a small voltage drop and behaves closer to short. So if we don't have enough time to get into the steady state or to get to that 5 volt, then the capacitor behaves closer to a short. So if this signal is oscillating very rapidly, the capacitor never charges or discharges or never quite reaches that V infinity value. Whereas in contrast, if the voltage is changing very slowly or we're at a low All right, so to reiterate it for a third time, so to approximate capacitors as short, we require that omega is greater than 1 over tau. And to approximate capacitors, we require that omega is less than 1 over tau. So of course, this translates to uh, omega c is greater than 1 over r. All right, so, okay, so this, this is kind of how we think about our, conceptually, how we think about our amplifier circuits. So this is the region where we get the gain that we want, or the AVI that we calculate using our mid-frequency or small signal model. And in the low frequency, so at the DC model, we treat all capacitors as open, but as we keep increasing the frequency, these capacitors need to actually be included into our calculations until eventually we reach this transition point where we can start treating them as shorts. And so that's where we get our mid-frequency. Okay, so what we're going to do, so basically what we said was that at DC we could treat all capacitors as open, and as a result our equivalent DC model was this. Now if you keep increasing the frequency, eventually you're going to be in a region where you're in between being able to treat these things as short as we do in the small signal, and here, so that's what we see here. This is the low frequency model, and as you can see, we've just basically taken our gate and transistor, our small signal model for the transistor, and we connect it to a circuit which now actually includes all of the capacitors. So you see here how the RSS ends between the it's between RSS are in parallel with C3 and then ground. So that's what we have here. And then what we have in connected to the drain is RD, which is then connected to ground. So RD and then connected to ground. And then you have C2 in series with RL, which is then connected to ground. So here you have C2 series with RL connected to ground. And if you look Okay, so here is our mid-frequency model, and to derive this mid-frequency model, as I said before, we just simply treated all of the capacitances as shorts. So this capacitance became a short, this capacitance became a short. So since this becomes a short, now the source terminal is now connected directly to ground. So that's why now this source terminal is directly connected to ground. And additionally, we no longer have the C2 in between the RD and RL, and there's no C1 here between the RS and VS. So finally, if you keep increasing this frequency, no longer we can actually neglect the capacitances associated with the um, transistor, and then we reach our high frequency model. And for a high frequency model, then we just simply have kind of the capacitance between the gate and the source and the capacitance between the gate and the drain. Now, notice something interesting. If this capacitor start behaving as short, we have a problem because now VGS becomes 0, and then there is basically no amplification. So at high frequencies, this doesn't work very well. So there's actually just a range of frequencies when you can treat these capacitors as short, external capacitors as shorts, caps as shorts, and between being able to treat internal capacitors as open, where you actually amplify. And in particular, we want to know at what frequency we can start treating these as short, or what we're going to call omega low, and at what frequencies we can start treating what we need to actually start considering the internal capacitance. And well, sorry, we need to go this way. And that's what we're going to call omega high. Okay, so just to reiterate, uh, we've been looking at this small signal model at the middle frequency, and to do that, we made an assumption, which was that we made two assumptions. One was that external capacitors behave as shorts, and MOSFET internal capacitances behaved as open. And as it turns out, that's not always the case. And the subject of this lecture is figuring out at what frequency we can actually start treating the external capacitors as shorts, and at what frequencies we need to start. We cannot no longer treat those internal capacitors as open. And so here's kind of the heuristic that we're going to use. So first, we're going to write our small signal model, but this time including all capacitors. So that's what I drew here. So this is the small signal model for this circuit, except capacitors are all included. And then specifically what we're going to do is we're going to use this heuristic where for each capacitor, we need to find the Thevenin equivalent resistance of a circuit that involves basically, if let's say we want to taking the initial capacitor, removing it, and shorting all other capacitors. So just to give you an idea, if I want to find the Thevenin resistance for C1, I would remove this resistor and I would look for R Thevenin looking into here, and then I would short out the other two capacitors. And then if I want to do this for C2, then I would basically remove this capacitor, look for R Thevenin looking into here, and then short out the other two. And then for C3, I would do the same thing, and I would come up with my R Thevenin 3. And then once I come up with those three R Thevenins, each R Thevenin gets multiplied by its respective capacitance to find the equivalent time constant of that circuit. So in particular, for this circuit, we're actually basically defining kind of an R Thevenin 1, C1 model for our circuit, then an R Thevenin 2, C2 for our circuit, and then on our Thevenin 3, C3 model for our circuit. And in particular, what we're going to say is that omega low is 1 over the maximum of each of these individual time constants. So in particular, what we're really looking for is kind of which one's at the highest end, what's the highest frequency at which one of these particular capacitors cannot be treated as a short. So what do I mean by that? Well, to be treated as a short, remember we said that R Thevenin has to be greater than 1 over omega c, which means that omega has to be greater than 1 over R Thevenin times c, or the time constant, or 1 over tau. And so basically, the first capacitor that will fail, or the highest frequency at which no capacitor fails, is kind of the maximum. So remember, omega 1 has to be greater than 1 over, for capacitor 1 to be able to be treated as a short, we need omega to be greater than R Thevenin 1 times C1. For omega 2 to be, for C2 to be treated as a short, we need R Thevenin 2, C2 to be greater than omega 2. So for omega to be greater than 1 over R2 C2, and then again, we need omega to be greater than R, to be able to treat C3 as a short, we need R3 times 1 over R3 C3 to be less than omega. Okay, so I might have said something, the inequalities are all correct, so remember, 1 over R3 C3, if omega is greater than that, then that means that we can treat capacitor 3 as a short. 1 over R1 C1, if omega is greater than that, that means that we can treat C1 as a short. So if we pick the largest one of these as omega low, that will guarantee that we can treat all capacitors as short if our frequency is higher than the highest one of 1 over R1 C1, 1 over R2 C2, and 1 over R3 C3. So that's effectively what we will do. So basically, we're just going to say omega low is equal to the maximum between 1 over tau 1, 1 over tau 2, 1 over tau 3. Okay, so just to reiterate, we're going to find the Thevenin resistance looking into each capacitor while assuming that all other capacitors are short. And then once we find those Thevenin resistances, we're going to define time constants for each individual circuit. And then we're going to pick the one associated with the highest frequency as our omega low. All right, so now I'm actually going to go over some problem solving because I think it's easier seeing it being done than actually explaining it heuristically. So I'm actually going to derive the R Thevenins for the individual circuits. And the three circuits that we're again interested in is the common source, common drain, and common gate. And here are actually the final solutions. In this video, I will only go over the common source. The common drain and common gate will be given in a separate video. And just to reiterate, once we find our time constants, which are just C times the R Thevenin 1, C2 times R Thevenin 2, C3 times R Thevenin 3, we just pick the 1 over the maximum. And in general, what we will find is actually that the capacitor connected to the source terminal, or C3 in this case, and the capacitor, or C2 in this case, and C1 in this case, is actually the one that's going to fail first, or the one that's going to be responsible for omega low. Okay, so again, just to reiterate, we have our small signal model, and then we're just going to assume that one capacitor fails, find the R Thevenin, so we treat the other two as short, and then once we find our R Thevenin, then we're going to move on to the next capacitor and the next capacitor until we're done. So we're going to start with C. Okay, so let's now look at how we can draw our equivalent circuit for C1. So in particular, what we said is we're going to remove this capacitor and we're going to short out all other capacitors. What that means is that now our source terminal will be grounded. So now we have our gate, we have our drain, and then we have our source. Now, you could have already noticed that we are not including any of the channel leg modulation in this lecture. The book decided to do that to make the analysis simpler, but in general, you would have channel leg modulation. So in this class, we just don't add it because we don't really want to make the math more complicated than it already is. That being said, it's still there. And if you take more advanced classes, you will probably consider it when you analyze these omega lows and omega highs. But in this class, we don't do that. Okay, so that's our circuit here. So I just wrote the right-hand side of the circuit or left-hand side, depending on what your convention is currently. And so this is R1 in parallel to R2. And then this is our terminal for C1. And then we have our sig. And remember that when we're finding Thevenin resistances, we typically will short out any sources. So this source will get shorted out. And so we're gonna be looking at our Thevenin into this particular terminal. So whenever I solve these circuits, I will always use a IX-VX test, even though you don't really need to do that in this case. You're gonna get that it's just R sig in series with R1 and R2. That being said, using a IX-VX test will always work, so that's why I always do it. So I'm just gonna insert an IX minus plus. So this is my VX, and then I need to figure out what IX is. Additionally, we have to realize that in this particular case, we don't have to worry about what VGS is because we're on the other side of the circuit, and so we don't really interact with that current, so we don't have to worry about it. So what we're going to do is we're actually going to use KCL here, and so we will have that Vx minus, so remember Ix is coming out of here, and then it has to go down here, Ix times R1 in parallel to R2, and then it has to also drop through R6, so it goes in that direction, so minus Ix R sig has to be equal to 0, and that's going to give us that Vx over Ix equals R1 in parallel to R2 plus R sig. So now remember that in your 2K1 class, you didn't put a Vx, you just put a 1 volt test source. So let's just say I put a 1 volt test source here, then this would just be 1, the Ix and Vx, the rest remains the same, and then I would find 1 over Ix, and that would be my R Thevenin, TH1. Cool, so now that we find our R Thevenin 1, we would just multiply by C1, and that would give us our tau 1. Okay, so in the next slide, this is done cleanly. So here I basically just drew out the same thing that I did in the previous slide. And as you can see here, I got the same thing for R Thevenin 1. So now let's go to find the second capacitor associated resistance. So to look at the second capacitor, now we remove this capacitor because we're going to be looking into R Thevenin 2 here, and we're going to short out all other capacitors. And then again, remember when we're looking for our Thevenin, we always short out any external source. So let's draw our circuit. So again, our source will be grounded. So we have here our source terminal, and then our drain terminal, and then we have GM VGS, and then we're going to have RD, and then we're going to have RL, and then this is going to be V out plus minus, and then here is our gate, and then now we have R1 in parallel to R2, and then R sig, and then this is shorted. Okay, so now we need to actually, oh, and remember that we needed to do R Thevenin here, so I shouldn't have drawn this line here. It should actually look like this. And then this is the R Thevenin location that we're trying to look at. In this particular case, we will first, so let's do our IXVX test. So I'm gonna insert my plus minus. This is IX and this is VX. So we need to know how much current is actually flowing out of GM-VGS. So in this particular case, we have that this is grounded, so this is grounded. And notice how here this is open, so there can't be any current flow. So this is actually also 0 volts. So VGS is actually 0 volts. Additionally, we have, so that means that this is 0 volts, so there's actually no current flowing through this current dependent source. And at this particular case, now we need to actually figure out what IXVX is. So we have, hold on, and I forgot to draw RL here, so there's my RL. Okay, so now we can do the loop equation. So we have Vx minus RL Ix minus RDIX. That should all be equal to 0. So we get that Vx over Ix equals RL plus RD. And again, in your 2K1, you would have put a 1 volt source here, which means there's a 1 here, which means there's a 1 here, and everything stays the same. We still get that our Thevenin is RD plus RL. We multiply that by C2 to get our tau 2, so tau 2 would be RL plus RD. And that's it. So here I basically show the same thing, but more cleanly, and now we're left with C3. All right, so to calculate tau 3, we again take our circuit, we short out all the remaining capacitors. Since we're finding our Thevenin, we can short out external sources, and then we just need our Thevenin 3, looking into here. So now this is a little bit more involved because now we have our sig, and then we have the R1 in parallel to R2, and then we have to maintain this RSS, and now we have, this is the terminal we're looking into, then ground is right here, and now we have GM VGS, and then this is our drain, this is our source, this is our gate, and then we have our RD and our RL, and this is kind of our circuit, and we're looking for our Thevenin, looking into this terminal here. So we're going to stick a Vx here. Oh, let me just redraw this because So we're going to stick our Vx here, plus minus Vx. And you know, whenever you have the dependent source, I don't know if you've already noticed this, the first thing I do is try to write VGS in terms of Vn and Vout, or between any kind of source in our circuit. In this particular case, since this is 0, and this is open, we know that Vg will actually be equal to 0. And additionally, we know that this is 0, so that means that this is Vx. So that means that Vs is equal to Vx VG equals 0, which tells us that VGS is actually negative Vx. Okay, now I actually can do, so this is Ix coming out of the source. I'm going to do this nodal equation here. And what that's going to give me is actually that negative Ix minus Gm times negative Vx, because remember VGS is negative Vx. And then I'm going to have, well, this is just Vx over RSS, so plus Vx over RSS. Oh, sorry. Plus Vx over RSS has to be equal to 0. And then I just move Ix to the other side, and I'm going to get basically that Vx over Ix equals 1 over Gm plus 1 over RSS. So that gives me that R Thevenin is actually equal to 1 over Gm parallel with RSS. And that's it. That concludes the common source R Thevenin 3. So now we can find our tau t by multiplying this by C3. And in this slide, I actually do the same exact thing as I did earlier, except more cleanly. So basically, we find out that Vg is 0. We find out that Vs is Vx. And then we do the nodal equation to get our tau 3. All right, now let's look at, so for our common source amplifier, these are the 3 taus summarized. And typically what will happen is that omega low will tend to be 1 over tau 3. And that's because 1 over Gm is smaller than all the other resistances. Okay, so now we're going to do our high frequency analysis. And just like we did for our low frequencies to compute the omega lows, we had basically a Thevenin resistance associated with each external capacitor. Now we're going to have Thevenin resistances associated with the 2 internal resistances capacitances of the transistor. So remember that our model was, this is the gate, this is the source, and then you have your drain, and then you always draw a current source pointing from the drain to the source, and GM, VGS. So remember that we had a capacitance between the gate and the drain, and the gate and the source, so we call the CGS, CGD. And so just like we did for the omega lows, we computed capacitance associated with each of the external capacitors. Now we're going to do the same thing for the internal capacitances. And so for each circuit, we're going to have a tau GS and a tau GD. We're going to actually derive these for the common source, the common drain, and the common gate in the next few slides. Yeah, so that's basically what we're going to do. And additionally, to compute omega high, instead of using the maximum of the two, we're typically going to use this formula, which adds them both up. So tau GS plus tau GD, 1 over that is going to be omega high. All right, so for high frequencies, since omega just gets bigger, 1 over j omega C1, 1 over j omega C2, and 1 over j omega C3 will be even smaller and smaller. So these external capacitors will continue to behave as short, so we don't have to worry about them. But as we keep increasing this frequency, recollect that what's going to happen is that we're going to have to start considering the internal capacitances. So for this common source amplifier, our circuit will still be, you have the gate, you have the source is what's shorted, you have the drain, you have your current source, and then you have that your R sig in series with V sig, so you have R sig, and now you have V sig. You have R2 and R1 in parallel, and then you have RD in parallel to RL. And remember that we are ignoring RO for this lecture, so that's why there's no little RO. And then RSS has been shorted out, so there's no more resistors to be derived. What's going to change is that now we actually have to start considering CGD and CGS. And so our heuristic will actually be, we will assume that both capacitors behave as open, and then we're going to look at R Thevenin looking here. And then once we find that, we're going to find R Thevenin 1, and then we're going to find R Thevenin 2. And whenever we're finding R Thevenin, we always short out any external source. So we're actually not in the low frequency case, we shorted out all other capacitors. Now we actually leave all other capacitors as open, because remember, we're always looking at things from the perspective of the mid-frequency model. And in the mid-frequency model, all external capacitors are short, and that's why we shorted them. And all internal capacitors are open, and that's why now we're just going to leave them open. All right, so here's kind of what I just said in the previous slide. So this is our small signal model, and what changes from this model to the high frequency is these two capacitances. And we're going to always be looking at this circuit on the top, and we're going to find the R Thevenin 1 and R Thevenin 2, or R Thevenin GD, in order to figure out our time constants, and then we're going to use those time constants to find omega high. Okay, so let's try to find the time constants for CGS. So to do that, we have to connect a source here, Vx. Well, hey, look, when we do this source here with Vx, we actually get that, well, this is connected between the gate and the source, so this actually becomes Vx. So that makes our life a little bit easier. And then this is Ix here. In this particular case, we have that Ix has to flow through these two circuits. And so we're going to have that basically, well, Ix is equal to, sorry, let's just do that node equation right here. So we have negative Ix. I got a little ahead of myself. Negative Ix plus Vx over R sig plus Vx over R1 in parallel to R2 has to be equal to 0. And that's just going to give me that R Thevenin GS, which is equal to Vx over Ix, is just equal to R sig in parallel to R1 in parallel to R2. That's it. Okay, so now let's look at, so now we're going to look at high frequency from this particular circuit. So now we're going to basically put a Vx test source here plus minus Vx, and then we have Ix flowing out of here. One thing to note here is that if Ix flows into this terminal, that means that it has to flow through these three resistors in parallel, which means that the voltage from here to here, which is actually equal to VGS, has to be equal to Ix times R sig in parallel to R1 in parallel to R2. So Ix flows into these three in parallel, and so that should be VGS. So now that we know what VGS is, now we just simply need to now we need to figure out how to write VGS in terms of Vx. So in this particular case, we have that we have that Vx is equal to VGD and remember that Vs is 0, so that tells us that and we know that VGS is actually equal to VG because Vs is 0. So this is actually equal to Vg minus Vd. So that tells us that Vd is actually equal to Ix R sig in parallel to R1 in parallel to R2 minus Vx. Of course, this is just Vg. And VGS is actually just equal to Vg. Okay, so now let's look at this node equation here. So what we're going to have here is VDS, which is equal to VD. So we have Ix flowing out through here, and then we have plus GM VG. We also have plus VD over RD in parallel to RL. So that would be these two currents. Okay, and that should all be equal to 0. So we need to get this in terms of Vx and Ix. So to do that, we can replace all of the VDs with this term and all of the VGs with this term. So we're going to get we're going to get 1 plus GM times R sig in parallel to R1 parallel to R2 plus so VD, we're going to have R sig in parallel to R1 in parallel to R2 divided by RD in parallel to RL. That all times Ix. And then we have to subtract Vx over RD in parallel to RL. That has to be equal to 0. And so we move all the Vx terms to the other side. So that's just going to give us that this has to be equal to that. We multiply out by RD in parallel to RL. So that's going to give us this. It's going to cancel out this one. And then this is going to be RD parallel to RL. And then there's going to be an RD parallel to RL. And then finally, we're going to divide out by Ix. And that's going to give us R Thevenin 1. So that's our R Thevenin GD. In the next slide, I do it more cleanly. So let's do that. So this is actually what I derived in the previous slide. And again, we have that Vx. It's actually equal to VGD. But VGD is actually VGS. VGS is actually equal to VGD minus VSD. And so we get that Vx minus VSD equals VDS, which implies that VDS equals VGS minus Vx. So in the previous slide, I just used the fact that Vs was 0 to get this. When we do this node equation, we're just going to get that VGS is equal to Ix with R sig and R1 and R2 in parallel. And then we have to do this node equation, and that's when we got this. And then we use this relation to replace with this one. And then we replace this relation with this one. And that gives us this equation, which is what I had in the previous slide. And then I just basically did a bunch of algebra to get to here. Note that I kind of did it fairly quickly. This is kind of a messy one, but it's not really that much more complicated than the other two cases.